Yeah, ma'am. We can go ahead, ma'am.
So you said I have to mute somewhere in. I don't think anyone has joined, no, Mahesh?
Yeah, ma'am. 3 of them is there.
Okay, we'll wait for maybe 5 minutes.
Sure, ma'am. Sure.
Yeah. Okay, good evening. We will start now. Mahesh, is everything all right?
Yes, ma'am. Everything all right, ma'am.
Okay. So, good evening, everyone, and welcome to this first interaction session. So, I hope you have viewed the lectures. So, first of all, let me take the questions that I see in the chat box right now. Lecture slides available, please, it will help us to revise. So what is available is the transcript. So the content of the lecture slide is already available in the transcript. Please take a look at that. All what is done in the lecture slide is given in the transcript. So please go through that. Then there were some questions in the queries that was in the feedback. And the first comment. I'm just reading out the question / comment there. So let me just read out what is happening there. I am a student who understands everything in a simple way. What suggestions do you give to make me feel this course is a simple one and understand it better? This course scares me. What tips you can give to boost my confidence in it? Previous years NPTEL statistics show very less students passing and doing well. What should I do? So I first of all tell you that this is not a simple course. No course is a simple course. It requires some work to be done. It needs background work to be done. You have the lectures, you have the best opportunity. You have the lectures with you, you have the references with you, you have the transcripts with you. Everything that I say in the lecture is given as notes to you. There are short questions for every video which you can use to check whether you understood the concept or not. Solutions are given to those short questions. And every week we are going to have this interaction session a day before the assignment submission. So you can try out the assignments and you can even come and ask me questions about these assignments. I will obviously not give you the final answer, but I will definitely help you how to solve these assignments. So the course requires some time that needs to be spent for it. Without that, it is not going to be easy. Okay, so the way to not get scared about this course is to be friendly to this course. So keep accessing the content, keep accessing the transcript material, keep trying the assignments, try to solve the assignments. And I am offering to meet you every week before the assignment submission. So tomorrow is the assignment submission. Today I am ready to meet. And you have to please come up with your difficulties in the assignment so that I can help you learn this course. Okay. So I hope that clarifies. The next question is about how does one do research on LDPC code and fiber optic communication? So LDPC code is already an established code which is accepted in the fiber optic communication domain very, very popularly. So there is, I don't think there's any research on LDPC code that can be done. What is possible is try to work out different types of coding, forward error correction codes, which are suitable for optical communication. So the next question is, I have just completed my MTech from MNIT Allahabad. If we want to do a PhD in the field of optical fiber, then which topic we can go for? There are so many different topics you can pursue in the area of fiber optic communication. So this course is not going to describe the research topics. This course is going to describe to you the fundamentals of fiber optic communication, which if you go through this course, it will expose you to the digital signal processing required, the physical layer features of laser diodes, detectors, and optical fibers. It will also describe to you the link design and so on. So you need to work with your research guide to find out what is the area of research that you would like to pursue. It again depends on what is your background. If your background is from communication, if your background is from physics, there are several research topics that you can choose from. Those are the questions that I see in the document. Now, if there are, okay, there is one more question here from Syed Zaid. This course is good for second semester students. Actually, many terms in the lectures have hardly heard these terms. So maybe it is not a good course for second semester students because, as I said, you need to have an understanding of signals and systems, some basic understanding of digital communication to be able to do this course. So it may not be a very good course for a second semester student unless you are ready to put in the extra effort, ask relevant questions, and I'm always happy to help and answering those questions. Okay, now I will wait for questions from you, or if you have any specific questions in the assignments, please feel free to ask. So the book is already, the reference book is already given in the course page. So it is Fiber Optic Communication Technology by Govind Agarwal, Gerd Kaiser. One of these books, any one of these books would help you find the content that I'm teaching. And anyway, whatever I'm teaching, I'm already writing in transcripts. If that is not understandable, if you have any specific questions, please post your questions. There are teaching assistants who are looking at these emails that you're posting on a daily basis, and you will get responses. So don't think that your question is silly and can I ask this or something. It doesn't matter. Whatever is your question, please send it as an email in the course page. The teaching assistants are there to respond. There are 2 teaching assistants for this course, and they will respond to your questions. Is there any specific assignment question that you would like me to answer? I am ready to do that. If there's any feedback about the assignment, you can let me know. So if what we can then do is to go through the assignment questions and try to find the answers for the assignment questions. So let's pick assignment 1. The first question says, which of the following range of wavelength is termed as optical C-band? And the answer, there is nothing to think about. These are definitions that are written in the standards, and that is 1530 to 1565 nanometer. Which of the following wavelengths fall under visible spectrum? So again, the wavelength of 400 to 700 nanometer falls under visible spectrum. So you can convert wavelength to frequency using C is equal to F lambda. So 400 nanometer is 400 into 10 power minus 9 meter. Your frequency is C by 400 multiplied by 10 power minus 9 meter. And you can take the speed of light in vacuum, meter per second, divided by 400 into 10 power minus 9 nanometer. Now, the range of visible wavelength is 400 nanometer to 700 nanometer. So you can calculate what is the frequency corresponding to 400 nanometer. Similarly, you can calculate what is the frequency corresponding to 700 nanometer. This is meters here. So that gives you the range of the frequencies corresponding to visible light. and you can check whether any one of those fall in the options that are given. There is a question here, will the exam questions be of the same difficulty as that of the assignments? So typically 50% of the questions in the exam are directly from the assignments and short questions. Okay, they are directly repetition of, I'm already giving away a big secret. 50% of the assignment questions that I will set, the exam questions that I will set, will be directly from the short questions and the assignments, which means if you are thorough with the short questions and assignments, you are 50% of the score you have already. The remaining 50% will be based on the concepts that are taught in the assignments or taught during the lectures. Okay. You can type here on the chat window whether it is a good idea for me to go through all the assignment questions, or if that is not going to be useful to you, I will not discuss. So there are 18 people watching now. If they have any specific questions, you please type that. But otherwise, please let me know if I can go ahead solving these assignment problems for you. As I said, I will not give you the complete solution, but I'll tell you how to approach the problems. If you don't want me to do that, let me know. So I see a comment, all questions. Can you please expand what do you mean by all questions? Okay, so I joined late. I think that the assessment is difficult for me. If you explain it, it is more useful for me and others too. Okay, so the feedback I'm getting is we want, please go through all the questions. So let me just go ahead and do that. So this is now the third question in assignment 1. Which of the following discoveries revolutionized fiber optic communication technology? So this one, I'm not going to give you the answer. You have to go through the lectures. There's just a memory based kind of question. There is nothing difficult about this. Fourth one, which of the following bands are used for Wi-Fi standard? This is again, I'm not going to give you an answer. You can even Google it and find out. But I think it was discussed in the class lectures also. So you have to go through the lectures. These are just recollecting questions, and these are important because these are some of the very basic things as a communication engineer you should know. So again, because there is no technical understanding required, it is just a kind of a memory. I would want you to actually go through the lectures and find out. Question 5, for a complex modulation system with a symbol rate of 5 gigabaud. So I hope you can see my screen. So symbol rate is 5 gigabaud. 5 gigabaud means 5 into 10 power 9 gigabits per 5 into 10 power 9 baud. Using 16-QAM modulation format. Now, 16-QAM modulation, you have seen the lectures where what we are doing in 16-QAM modulation is you take a sequence of 110, this is the, let's say, the binary sequence that you want to transmit. In 16-QAM modulation, what do? You choose 4 bits and represent it as a symbol. There are, in the 16-QAM modulation, you have the constellation space with 16 possible symbols, and each of these symbols are representing the bit sequences 0000 up to 1111. So there are 16 possible combinations of symbols which this 16-QAM modulation is trying to represent. So for example, 1101 could get represented by this symbol, and so on. So which means that in each symbol duration, you are actually transmitting a particular amplitude value and a particular phase value corresponding to that symbol. So in one bit, in one symbol duration, you are transmitting 4 bits, right? The 16 came from 2 power 4. So the question is, how many bits are, what is a bit rate? So 5 gigabaud is the symbol rate. So this is 5 into 4. That must be your bit rate. Now, instead of 16 gigabaud, let's say if it is 32, instead of 16 QAM, let's say if it is 32 QAM, how do I find the symbol rates? If it is 32 QAM, it means that there are 32 constellation points. Now, what does this constellation point mean? Each point represents a certain amplitude and a certain phase value. So this is the complex plane. This axis represents the in phase, and this axis represents the quadrature. So this we have discussed in class, but just let me just repeat. So if I can represent a complex number by x plus jy, or equivalently as r e power j theta, this length of this vector represents the amplitude, and this angle it makes with the x-axis represents the phase. So if I have a 32 QAM constellation, I am choosing 32 unique points in this constellation space to represent my symbols. Now, if I have 32 unique points, it means that I could actually transmit a bit sequence from 32 different bit sequences, independent bit sequences. So it could be from 00 this to up to 1111, right? So you could have 00001 and so on, right? So you can think of representing each of these bit sequences as a particular constellation point in the 32 QAM, which means that every symbol is in 32 QAM is representing how many bits? It is 2 power 5 bits, which makes it 32. So every symbol is represented by 5 bits. So if my symbol is getting transmitted at a rate of, let's say, 5 gigabaud, it becomes baud because it is symbol rate per second. Then this has to get multiplied by this 2 power m, right? So this m to find out what is the net bit rate. Okay, so I hope that is clear. Again, I will not tell you the answer, which choice is the correct answer and all that, but this is the idea. The next question, number 6, is let's see if there are any assignment 2, question 16. So we will go one by one. So we will hopefully reach assignment 2, question 16 very soon. We are at assignment 1, question 6. Which of the following statements are factually incorrect? This again, I will not tell you the answer, but I can tell you the concept. The digital communication requires more processing than analog communication. We did discuss the differences between digital and analog communication. So you should go through the lectures to find out whether this is true or not. All natural signals are analog in nature. Again, this is probably the opening sentence of that lecture. So you can find out again by going back to the lecture. In a QPSK system, the baud rate is greater than or equal to bit rate. So this concept you just got. So QPSK is nothing but 4 QAM. That's what you're calling as QPSK. And that will have 4 constellation points, which means 4 QAM would mean 2 power 2. Multiplicity is 2. So from this, you know whether this choice is correct or not. FSK is widely used in optical communication. Again, please listen to that lecture. I have specifically said whether this is correct or not. Okay. The next question is about 8 PSK, the effective bit rate. So 8 PSK is 3 bits. So 8 PSK will correspond to 2 power 3. So now you can find out what is the relation between bit rate and symbol rate. Which of the following has the highest spectral efficiency at the Nyquist sampling rate? So we talked about Nyquist sampling rate. So in the lecture, please go back and see that. So if you have 16 QAM modulation, let's take one example at 10 gigabaud with non-return to zero modulation, which means that each of your symbol is represented by a non-return to zero signaling. So this looks like a kind of a square, so its Fourier transform is sinc, and so in the frequency spectrum you have something like this, and this is your bandwidth. So you have this as your bandwidth, and then if it is 16 QAM and 10 gigabaud, you know what is the bit rate. Bit rate is 10 gigabaud multiplied by it's 16 QAM, so the multiplicity is 2 power 4. So 10, this is 10 times 4, and it is gigabaud, so this will be 40 gigabits per second. And how do you define spectral efficiency? Spectral efficiency is nothing but its units is bits per second divided by hertz. So whatever is that capacity, 40 gigabits per second divided by what is the occupied bandwidth. And you have to be a little careful here. When you say Nyquist sampling rate, we discussed that you really need only a bandwidth of half of this for Nyquist sampling rate, right? So because it is Nyquist sampling rate, what you will need is the occupied bandwidth is only half of this, which means you will have only B. Now, what does this B get decided by? It is getting signal. The symbols are getting on and off at 10 gigabaud, which means this B is 10 gigahertz. The first null appears at 10 gigahertz. This appears at, so this is your zero frequency. This is at minus 10 gigahertz, which means the total bandwidth, if I consider from null to null, is 20, but Nyquist bandwidth is 10. So this is 40 gigabits per second divided by half of this separation, which is 10 gigahertz. So I get 4 giga, of course, is 10 power 9 in the numerator and the denominator. So you get 4 bits per second per hertz. So this is how you calculate the spectral efficiency. And I have given you an example of calculating this at for one choice. Now you can go ahead and calculate it for all the other choices, right? Let me see, there are some other questions. Can you plot? Okay, this is about question 18 in assignment 1. So that we are going to do. After the end of the assessment, can you please send the answer as a PDF like a written notes? Yes, it is being already ready. Once the assignment dates are over, the answer will be given to you. Okay, so let's just get back. The next question is, ADC has a sampling frequency of Fs. N is the quantization levels. The effective bit rate is given by this. So let's again revise. An ADC is taking an analog signal and it is digitizing. and it is digitizing by sampling at every fs frequency. So at every frequency, it is generating these samples. And how many levels is it generating? So let us say there are n quantization levels. It simply means that, let's say there are 3 quantization levels. Now these 3 quantization levels can be represented with 3 bits. So you can find out for n quantization levels, how many bits does it represent? How many bits? So if I were to represent this level, so let's take the case of 3. So this will be represented by 0, 0. Sorry, this is 4 levels. So there are only 2 quantization levels, 0, 0, 0, 1, 1, 0, and 1, 1. So I have taken the example of n is equal to 2. So of course, you will have to work out this problem for not n equal to 2, but for n quantization levels. Okay. So for every fs sampling rate, you get 2 bits in this case. So now you can find out, you get 1, 0. You need to transmit 1, 0 for every, let's say you are doing the sampling at 1 hertz sampling you're doing, which means every 1 second you are transmitting 1, 0, right? So if the sampling is at 10 hertz, it means that you need to send, you can think of finding out at what rate you need to send so that you're able to send 1, 0. Now this we did for n equal to 2. So now you can think of doing the same calculation for n is equal to n quantization levels. Okay. So let's say there are 4 quantization levels. So let me solve this problem for n equal to 2. If there are 4 quantization levels, then number of bits required to represent 4 quantization levels is 2. Because it could be 0, 0, 0, 1, 1, 0 or 1, 1. Now if you have n quantization levels, so how did I get this 2? I can imagine that 2 power 2 is actually 4. So if I have n quantization levels instead of 4, I can, this is going to be 2 power some m. So the number of bits must be, how many bits should represent n levels? So I need to find out m. So how to find out m? I take logarithm on both sides. So I get m log 2 to the base 2. I'm taking logarithm to the base 2 because it is 2 power m is equal to logarithm of n to the base 2. Now log 2 to the base 2 is 1. So how many levels do I need? It will be logarithm of n to the base 2. So that gives me the number of bits. Now remember, these number of bits have to be sent at this sampling rate. So the sampling rate could be, sampling frequency could be a certain, you could have a certain sampling frequency. So which means how fast should I send my signal? So if there is only one sampling frequency in every 1 second, it means I need to send only 1, 0 in every 1 second. So I need to have, but if it is fs as my sampling rate, then this should get multiplied by fs. So that is how you will calculate the bit rate. There is also one more question. Is it possible to arrange this in a Google Meet platform? That is something that NPTEL has to answer. I have no control on how this is arranged. This is arranged by NPTEL. So, but I will put forward this question to them. Any reason why you want it in Google Meet platform? You can probably, that will make it more interactive. You can ask your own questions live. So other than that, if there is any reason, just let me know. I will check with NPTEL team if that can be done. Okay, so we are moving to the next question. Number 10, which are the following factually incorrect relation? X-axis is for an analog signal. So that we have already marked here. So this is my analog signal, let's say. X-axis is time, Y-axis is voltage or amplitude, which is amplitude, which is quantized to n levels. Okay, and you are picking sampling at specific frequencies, Fs. So you can now see x-axis is discretized in quantization, y-axis is discretized in sampling. So you can now choose. X-axis is time axis, so you have to discretize in sampling. Y-axis is voltage axis, that has to get discretized in quantization. So you pick the right choice. The next one is the number of photons in a pulse of duration 1 nanosecond. So you have a pulse whose duration is 1 nanosecond. You want to know how many photons are getting released. Okay, but the information that you have is 1550 nanometer, and the power is 1 milliwatt. Now we know the energy of a photon is h nu. This is high school understanding. So energy of n photons is going to be nh nu. These n photons, so let's say this pulse has n photons, and these n photons are constituting the energy of this entire pulse. But I know the power, but I also know that power is energy, rate of consumption of energy. So energy per time, so joules per second, that is n watts. So how do I convert this information that I have in terms of power to energy? All what I need to do is to find the energy in the pulse. Is I know the pulse duration, so I just multiply and assume it is a rectangular pulse, right? Make that assumption, multiplied by pulse duration, which is 1 nanosecond. So you have 1 milliwatt multiplied by 1 nanosecond. You know what is the energy. Now the number of photons is energy divided by h nu. So you already calculated the energy of the pulse divided by energy of one photon, where h is your Planck's constant, 6.634 into 10 power minus 34 joule second. Nu is frequency, and we know C is equal to nu lambda or f lambda. So nu is equal to C over lambda. So you plug in the units correctly. Nanometer is 1550 into 10 power minus 9 meters. Always do all calculations in SI units so that you're not making any mistakes. 1 milliwatt is 1 into 10 power minus 3 watts. So you can use these relations and find out the number of photons. The reason why we are doing this problem is to actually try to point out one thing. It may happen that the number of photons is a fraction. So you round it off and say, you don't really round it off, you choose the closest integer and say that that's the number of photons. Later during the course, we will learn about what is the meaning of having a fractional number of photons. What does it mean? We will talk about this when we talk about short noise in a detector, probably in the 5th or 6th week or something, 6th or 7th week. Okay, so the next one is related to the question that I had solved earlier. What is a modulation format you would pick if you had to transmit 50 gigabits per second, but a symbol of 25 gigabaud? So I already explained to you how to calculate the symbol rate and the bit rate. So you use the same idea. The next one is power from a transmitter is 1 milliwatt. It is propagated through 100 kilometers of fiber. So let's just draw the block diagram. I have a transmitter, I have a fiber, I have a receiver. Okay. Always try to visualize what is happening. It becomes much easier to comprehend. Okay. It is propagated through 100 kilometer fiber. And what is given? It is given that it is an attenuation of 0.2 dB per kilometer. Which means that, so this problem is to just help you familiarize with the decibel scale and the, the linear scale. So if it is 0.2 dB per kilometer, when the signal goes through 100, it traverses 100 kilometer of fiber, the net loss would be 100 kilometer multiplied by 0.2 dB per kilometer. So that will be about 20 dB. Now 20 dB is a fraction of 100. It's a factor of 100 because 10 log 100 is going to be 20. So that's a conversion from linear unit to decibel units, right? So this is in the 100 in the linear scale. It is given that the power from the transmitter is 1 milliwatt. I know the loss here is 20 dB. I want to know what is the power here. So what I do is first, let's convert this 1 milliwatt to dBm. dBm is power in dBm. This we have done in class, but I'll just repeat. 10 log to the base 10 power in milliwatt. This m in this dBm indicates that you have to choose your power in milliwatt. So 1 milliwatt is 10 log of 1. So that is 0 dBm. 0 dBm doesn't mean 0 power. It means 1 milliwatt of power. So this is 0 dBm. And why are we doing this in the log scale? We are doing this in the log scale so that the calculations become simpler. So 0 dBm, there is a loss of 20 dB. So the resultant receiver becomes transmitted power in dBm minus loss in dB is your received power in dBm. You can just subtract. But if you're doing it in the linear scale, the other way of doing it is 1 milliwatt gets lost by a factor of 100. So this becomes 1 by 100 milliwatt. So this is 0.01 milliwatt, which is nothing but 10 microwatt. And again, I can directly write that 1 milliwatt is, my answer should be in dBm. So 1 milliwatt is 0 dBm. So 0.1 milliwatt will be minus 10 dBm because it is one order of magnitude lower, and 0.01 would be minus 20 dBm, right? So both the answers would come out to be the same. So this is again to familiarize you with the this calculations. There's a question, there's a comment here which says that please make the question somewhat simple. Believe me, these are the simplest questions that you want to answer when you're learning this course. It can't be simpler than this, okay? If you're writing, if you're doing memory-based questions, you're really not learning anything from the course. So if you really thinking of learning something from this course, please do questions as simple as what I have put in the assignments. Yes, for interactive session, you wanted it to be Google Me, but if you have doubts, you want to text, but there is a mic. That is right, but try to text and ask your questions in this chat window. Okay. The next question is again identical to what we did earlier, so I'm not going to repeat here. There is an FS given. There is a 3 bits in each symbol, so you can choose to manipulate those numbers to find out the baud rate and symbol rate. The next one is sketch the variation of power with time for on-off keyed non-return to 0 bit stream. What is the duration of the shortest and the widest optical pulse of this bit stream? So let's try to solve this. So I have a bit stream which is 10 11 00 111 01. This is to visualize how the bit stream is looking like. It is on off keying, meaning that, and it is non-return to 0. It means that whenever there is a 1, it is 1, and 0 would mean a 0. 1 1, so you have 1 and then again a 1, so it is not returning to 0, it is again a 1. Then you have a 0 and a 0, and again 3 ones, so you have 1 1 and 1, and again a 0. So after this you have a 0 and then you have a 1. Okay, so this is how the bit stream is going to look like. What is the duration of the shortest and the widest pulse? So which is the widest pulse? You have the widest pulse here because all these slots are the same. And what is the slot duration? This is a 1 Gbps. So which means 1 gigabits in 1 second, which means 10 power 9 bits in 1 second. So 1 bit will appear in how many seconds? 10 power minus 9 seconds, which is 1 nanosecond. So each of this duration is 1 nanoseconds. So the shortest pulse is here, which is 1 nanosecond. The longest pulse is 3 times 1 nanosecond. Question 17 is you have to identify ASK, PSK, BPSK, QPSK, and probably multi-level QPSK. So again, this is something you need to look at the lectures and you can immediately identify them. The last one, somebody had a question about this one. It's a very interesting question, very practical question, right? This is a thing, right? When you do a course, you want to be able to do some calculations for very, very practically useful systems, okay? So conventional CDs are used for voice recording. They employ a sampling rate. So FS is given to be 44.1 kilohertz. So this is the key, right? I mean, we are trying to solve a problem. First of all, try to, if there is a visualization, try to draw a picture. There's no visualization, just try to write the data in terms of the parameters that you know. Okay, so this is 16-bit quantization, which means that there are 2 power 16 levels, which means that every sample, so there's some analog signal, every sample, so this is my time axis, this is my voltage axis, every sample gets represented by a number which is represented as 16 bits. So which means that you sampled it and you wanted to send this information, you have to send 16 bits. Okay. The maximum allowable recording time is 75 minutes. This is for a CD. 75 minutes, 30 seconds. This is what a standard CD is. So total duration, so if this is the music that you're trying to record, the total duration of the music is 75 minutes and 30 seconds. Right, the total duration is 75 minutes, 30 seconds. So you can convert that into seconds. So this is 75 into 60 seconds plus 30 seconds. So this will come out to be some 4530 seconds. This is a standard for any CD. Okay. Now, every 8-bit of voice data is encoded as 17 bits, which is 8 bits of voice plus 9 bits for error correction, which means What it means is that whenever you are recording voice on a CD, you know that so let's say I am singing and this is my the voltage signal that I produced in the microphone. You sample this, you find out what the the number of bits are or the value of the bits are, and you write it on the CD. You use a laser to on the surface of the CD, use a laser to mark a 0 or a 1. But what happens is, it's very likely that the CD gets scratched and some of the bits actually disappear. So to avoid that, you have error correction codes. So for every 8 bits of voice that you are using, 9 bits is actually error correction codes, which is building some redundancy into the data that you're transmitting. Okay, so now one more information is given is, of course, 8 bits is equal to 1 byte. You have to find out what is the storage size of the CD. So how do you do that? So you know what is the total duration. You want to find out whether the CD is 400 MB, 300 MB, 200 MB, 800 MB, whatever it is, right? So you know what is the total. So we just calculated what is the duration. And you're sampling it at what rate? Your sampling frequency is given. The sampling frequency is 44.1 kilohertz. So how many samples are you producing per second? You have 44.1 kilohertz as your sampling rate, which means total number of samples that you are generating is 4530. Every second has 44.1 kilo samples, and you have to record 4530 seconds worth data. So this is 4530 multiplied by 44.1 into 10 power 3. Where did I get this from? This means that this is 44,100 per second, samples per second. So this is a large number. Okay. Now, how many bits of digital data? Each of these sample is representing how many bits? It is 16 bits of samples. So digital data corresponding to, or digital data corresponding to this is, so this is total number of samples, these many samples per second. So this is 4530 into 44.1 into 10 power 3 multiplied by 16 bits, because each of these sample is represented by 16 bits per second. Right? Now you can convert this into megabits per second. This is bits per second, and there is a conversion given from bits per second to megabits per second. Now, out of you also need, so 8 bits of voice plus 9 bits of codes. This is what is making your total. Remember this voice. See, this 4530 seconds was voice. Look at the beginning of the question. It says it is used for voice recording. It employs this. The maximum allowable recording time is this much. So this much 4530 seconds worth voice you have. But it's not sufficient for me to just send the voice, right? I have to send the 9 bits for error correction also. So how much? So this let's say is M or some X Mbps. Do that calculation, right? So this has to get multiplied by 9. It's not only voice you need, but 9/8 of that is error correction. So whatever is my X multiplied by, so it's like saying I have X plus 9/8 fraction of this is actually error correction. So that will be my total capacity storage size of the CD required. Okay, so I hope yeah, Karthik says that loss is equal to minus 10 log P out by in. We could use the formula in the previous problem. Yes, you can use the same formula. That is right. It'll give you the same answers. Okay. So this is about assignment 1. Now we move on to assignment 2. Unless there are questions from assignment 1. So in assignment 2, the first one is again lecture based. So you please go through the lectures to answer the first one. The second one is a very important point, and it's a very fundamental point as far as semiconductor laser sources and detectors are concerned. You cannot make, this we discussed in class also, you cannot make semiconductor sources with silicon because silicon is indirect band gap material. So if you look at the EK diagram, energy band diagram, E versus energy versus momentum, you have this as your band diagram. A transition happens only when it satisfies. A transition from a conduction valence band to the conduction band happens only when it satisfies energy conservation and momentum conservation. So at the, if the the lowest energy level of the valence band and the highest energy level of the conduction lowest energy level of the conduction band and the highest energy level of the valence band, if the K values are matching, then there cannot be a transition. This transition cannot occur. So there cannot be emission. So which is why silicon, which is an indirect band gap material, you have to always remember that indirect band gap materials cannot release photons. Okay. So the next one is actually a completely formula based question. So you can actually look the reason why some of these questions are given is to ensure that you are going through the contents thoroughly. Okay. So a double heterojunction LED is emitting at a peak wavelength of 980 nanometer. Drive current is, so let's just write down the data. Lambda is 980 nanometer. Drive current is 100 milliamps. Internal quantum efficiency is 50%. And the radiative recombination time of the minority carriers is tau radiative is 60 nanoseconds. And the refractive index is 3.5. So the first question is total carrier recombination. So you know internal quantum efficiency is decided by tau radiative and tau non-radiative, which is tau total, which is tau effective. So you can look up the relation, and you have 2 data points. You need to find out the third one. Power of the generated LED also we have derived in class. You can find out. So basically the power will become the slope efficiency multiplied by the current. Slope efficiency was derived in class in terms of eta internal, in terms of HC by E lambda. So you can actually find out that relation, substitute. It just requires careful substitution in SI units for all these numbers. There is no trick here. Question 5 again, there is no trick. We have discussed in class optical electrical bandwidth relation is a very direct question. Question 6 is use of the relation given in question 5. Electrical bandwidth is given, find the optical bandwidth. So you just have to, this is all derived directly in class. There's absolutely no confusion. You just have to make sure you're listening to the lecture in the class and pull out the formula. The next one is interesting. I mean, this is again a concept that you need to know. It's just, again, there's no complication. You are using indium, gallium, arsenide, phosphide, indium 1 minus X, gallium X, arsenide Y, phosphide 1 minus Y. X is given to be 0.4. Y is equal to 2.2 times X. And see, the idea is to drive home the point that this is a heterojunction. It's a compound semiconductor. The sorry, this is not a heterojunction. Sorry, this is just a quaternary alloy, which means that this is an alloy which has 4 components, 4 elements which form the alloy. And the point that we are trying to drive home is that the band gap of this material is decided by the fraction, the molar fraction of which is denoted as X and Y. And that relation is given to you. So you can find out what is the operating wavelength of this device, given that this is the band gap. So you, from this band gap expression is given to you, substitute for Y and find out what is the value of band gap. So find EG for X is equal to 4. X is equal to 0.4. You can find out that. Once you know what your EG is, we know that, you know, we derive this empirical relation, or this relation 1.24 divided by EG, where EG is in electron volt and this answer will be in nanometer. So use this relation and find out what is the wavelength of operation. The next question is again related, carrier lifetime and what is the bandwidth. So that relation is known in class. I mean, how do you relate bandwidth and carrier lifetime? We derived that in class. You just have to use that relation. Similarly, find the full width at half maximum. Again, this was derived in class. It's just a repetition of what is there in class. I mean, there is no trick. And in fact, the exact answer was derived in one of those lectures. The next one is about, again, another question with similar data given. So it's more or less repetition of the previous 5 questions. The small change is that there is some injection rate that is asked. Now, what is carrier injection rate? Carrier injection rate is the rate at which you are injecting the carriers. So how do I find the carrier injection rate? We use this while writing the rate equation. We say if the current is I and the charge of the electron is E, it means that there are I electrons that are injected per second. So the number of charges that are injected can be found just by dividing the current with E. So that's a very straightforward thing. Then optical power. Optical power, like what I said earlier, it is slope efficiency time. So this is optical power. Slope efficiency times I. You have all the data corresponding to what you need to find slope efficiency. Internally is, you know, you have to now look at external quantum efficiency and internal quantum efficiency. And we have derived what exactly is the external quantum efficiency in terms of the refractive index. So you use that relation. And similarly, slope efficiency, that also we know. Wall plug efficiency is output optical power divided by electrical power consumed. Our output optical power you would have calculated by using slope efficiency. Electrical power is voltage times current. So the bias voltage and current is given. So from that you can find out the ratio of output power divided by electrical power. Spectral width, it is a repetition because you know the spectral width of an LED, no matter what LED you use, it is the same. The next question is about a Lambertian source. So again, we discussed in class that whenever an LED makes a emission, the emission is Lambertian. This is the radiation pattern of, or radiation plot of the LED. What does it mean? So this is the let's say this is true for any LED, unless you do something to modify this. So here the surface that I'm marking in dark is the emission surface of the LED. At theta equal to 0, the peak power is or intensity is I naught. The Lambertian source means that if you measure the intensity at an angle theta, this is I naught cos theta, which means if I measure at 90 degree, the intensity is going to be 0. So this is how the Lambertian source works. Now, if this LED is allowed to fall, if the light from this LED is allowed to fall on a wall at a distance 1 meter. So let's just, again, as I said, let me repeat, it will always be a good idea to visualize what is happening. So you have a wall which is at a distance of 1 meter. So here is the wall, and here is how it's going to look like, right? So you want to know, at what, if this light is allowed to fall on at a distance of 1 meter, what is the area that is illuminated? Okay, so you can calculate what is the angle at which the intensity drops to 0, and you can find out this surface area. That's the area that's getting illuminated. I hope this is clear. Light from the LED is allowed to fall on a wall at distance 1 meter. The area in meter square of the wall where the intensity, where the intensity is at least half the peak intensity. Sorry. So the question is, let me just rephrase the question. This is the radiation pattern of the LED. You want to find out, so here is my wall, the red line is my wall. So here is the peak intensity, I naught, and I want to know, I'm just drawing the 2D surface or side view here. At a particular value of theta, the intensity will fall to 50% of its peak value. So where would the I naught, where would it become I naught by 2? Okay, so, and you know I is equal to I naught cos theta. So when would I become equal to I naught if you consider it as a function of angle? I mean, when cos theta becomes half, that is corresponding to theta equal to 60 degree. So at theta equal to 60 degree, now you want to know what is this radius. This is 1 meter, you know. The distance from the source, you know, is 1 meter. So you can find out what is tan theta is equal to r divided by 1 meter. And you know this angle is 60 degree. So you can find out r as tan 60 degree. And the radius of this patch is pi r square. So from that you calculate what is the area that gets eliminated, such that the intensity is 50%. Laser is preferred over LED. We have discussed in class, go through the lecture. Lasers have higher modulation capability. Again, we have discussed in class, you have to go through the lectures. So that completes the assignment 2. There's a question, is the slope efficiency and responsivity the same? No. So slope efficiency, that's a good question. Whenever you use a LED or a laser, you send a current, and so you get electrical in this is current, and the output is power optical. And we have learned in class that this Li curve or optical power versus the electrical current. So this is usually in milliamps and this is in milliwatts. For an LED, it's going to look like a straight line passing through the origin. And for a laser, we have learned that it is going to have a threshold. So the slope of this is what is called as the slope efficiency. How efficiently is the laser or LED working? In the sense, how much optical power am I getting for a unit electrical current? And this is in the unit watt per ampere. Now, responsivity, so this is slope efficiency. Responsivity, on the other hand, is a parameter for a PD. So, photodetector. We will talk about photodetector and we will derive the responsivity in probably week 6 or something. But I'll tell you, photodiode is nothing but a reverse biased PN junction. So I should draw it this way. This is grounded and this goes through a resistor. Current gets generated when P optical falls on it. When optical power falls on the photodiode, there is a current that gets generated. Now, this dependence, how much electrical current gets generated when optical power falls on it, that slope gives you responsivity. And that is measured in ampere per watt. So essentially, slope efficiency is a quantity that characterizes the laser, whereas responsivity is a quantity that characterizes the detector. So I hope this is clear. So we have completed discussing all the assignments. So this is what we will do every week. We will meet a day before the assignment, and I strongly urge you to try out all these questions. Otherwise, you will not be able to understand and appreciate what I'm saying. So during this contact hour, we will discuss ways to solve this assignment problems. If you have any questions, you can obviously ask them. But the session will be useful only if you have gone through the lectures, studied the transcripts, attempted the short questions, attempted the assignments, and then you come and sit here, it will be of use. And this is how the course becomes easy. Okay, so I'll wait for a couple of minutes if there are any other questions. If not, we will close. So Mahesh, I'm not seeing any questions, so we can stop the session.
Sure, ma'am. We can wind up the session.
Yes, thank you.
Thank you, ma'am.
So we will have it every Wednesday around the same time, unless there is very strong feedback that this time does not work. So please send that as a feedback also if there is some other time that is most suitable. I thought the day before the assignment is best because you would have enough time to try out all the questions, and then the session becomes useful. Okay, thank you so much.